In this video, we're going to have a crash course one-page introduction to Bayesian statistics, so we can check out a third example of the Metropolis-Hastings algorithm. And if you haven't seen Bayesian statistics before, it's good to have a little bit of familiarity with this. So for this, we need to kind of identify two major worldviews in statistics, or two main philosophies of statistics. I will jump down here and say these two camps have been at war with one another for a long time. More recently, Bayesian statistics has been able to actually be put into practice because of computational power. But they've been kind of two competing viewpoints. However, recently, people are seeing the benefits of using both of these, especially since we have, again, more computational power. So what are these two viewpoints? The first one, the frequentist viewpoint. It's likely that this is the only one you've ever seen, that you've been working with your entire statistics career. So it views population parameters as real unknown values. We do hypothesis tests and confidence intervals trying to estimate the mean of the population, and that implies that the mean of the population is some fixed real value that's out there that exists, and we're trying to pin it down and estimate that fixed value that's out there. So emphasize here, parameters are fixed values. Okay, that's very much in contrast with the Bayesian viewpoint. The Bayesian viewpoint doesn't view parameters as fixed. It views parameters as simply an abstraction, and the data are the only real thing. Parameters are some abstraction we use to describe and understand the data, and some values of the parameters are more credible than others, but they're not something we can pin down. It's just an abstraction. Some give us more credible, realistic values to describe the data. So the important part here is that in the Bayesian viewpoint, parameters themselves have a distribution. They're not a fixed value to be pinned down. And that distribution of the parameters also would have parameters, and those parameters would also have parameters, and so on. This is a big rabbit hole in Bayesian statistics, this whole distribution on the parameters and hyperdistributions and so on. And we're going to kind of avoid that here, but it's out there. So the big idea, to sum this up, frequentists view parameters as a fixed, actual, real value to pin down. Bayesians view parameters as having a distribution of themselves, describing which values are more or less likely based on the real data. Okay, so let's look at kind of the mathematics behind this. So it's just a reminder of your kind of basic probability. We had this formula, probability of A and B is probability of A given B times probability of B, just that general multiplication rule for probability. So that's all we're doing, is we're applying that in our context of the data, x, this is some vector, and theta, this could also be a vector of parameters. So the joint distribution, or joint probability distribution of our data and parameters, note both of these are random, is equal to our A given B, in this case the data given a given parameter. This is called the likelihood function. So the probability of observing data for a given value of the parameter times f of theta, or the distribution of our parameter. This is called a prior distribution, and it describes our prior belief about what values of theta are more or less likely. All right, what we are most often interested in is not any of these pieces. Some of these are going to be our tools. What we're most interested in is this guy, our posterior distribution. So it's worded here. So our posterior distribution, we're going to use Bayes' rule. If you need to look it up real quick, pause and go for it. But using Bayes' rule, we get our posterior distribution is our likelihood function times the prior distribution, and we've got that law of total probability, or in other words, you can think of it down here as our normalizing constant in the denominator. And we've had a theme lately of who cares about the normalizing constant. It's just a constant. So I'm going to toss that out and say the posterior distribution is proportional to the likelihood distribution or likelihood function times the prior distribution. All right, why is this posterior distribution of interest? Well, remember, if you're a Bayesian, you're interested in theta. What's the distribution of theta? It's not a fixed value. It has a distribution. Some values of the parameter are more realistic or credible than others, given a particular set of data. So Bayesians are interested in this posterior distribution, probability of observing different values of the parameter given a particular data set. So kind of hitting that home here, rather than estimating a fixed parameter, Bayesians are interested in modeling the distribution of theta based on that prior belief. That was up here, our f of theta, and 2, the data, the likelihood of the data given a particular value of theta. So at the bottom, I'm going to just rehash one more time and kind of put this golden rule for Bayesian statistics here. So f of theta given x, so this is a function, the variable here is theta. And again, this is our posterior distribution, is proportional to f of x given theta. This is our likelihood times f of theta. This is our prior distribution. So if you don't remember anything about Bayesian statistics, if you remember just one thing, remember this relationship coming from Bayes' rule. Distribution of the parameter given some observed data is proportional to our likelihood function times the prior. And the big difference between Bayesians and frequentists, Bayesians believe the parameters are just an abstraction and they have their own distribution to describe more realistic values. Frequentists believe that the parameters are actual real values that we can pin down and estimate. So in the next video, we'll see how this applies in a particular example.